Yeah, so this story, because of, tomorrow is, of course, Independence Day. I was not expecting a lot of you people to show up, but you showed up, you braced the rain. So I'm going to tell you a story here about the two animals, very interesting ones. It was about the elephant and also the hyena. And then they were arguing, now, Mr. Lion, actually, you're not the king of the jungle. And then the lion said, who do you think is the king of the jungle? They said, no. It must be somebody else. No, the king of the jungle is another animal, and I won't mention the name. So, and then the lion said, in order to verify this, we've got to go out to the jungle and try to ask all the other animals who is the king of the jungle. So they went to the big ones, for example, the tiger. And then the lion would ask the tiger, Mr. Tiger, who is the king of the jungle? And then the tiger with its long neck would bow down a bit and would say, oh, Mr. Lion, you are the king of the jungle. And then, of course, the lion was satisfied and very happy, and then he looked at the hyena and said, you see, I am the king of the jungle. Then we went to the rhinoceros also, the same kind of story. The rhinoceros also confirmed that indeed the lion is the king of the jungle. Then they went on to the last one, and that is the elephant. And then the lion actually roared and asked, Mr. Elephant, who is the king of the jungle? And then the elephant looked at this guy and was actually wondering, why are you wondering who is the king of the jungle? So immediately the elephant poked up the ears like this, dashed to the lion, grabbed the tail, and started swinging the guy around, and then scratched him on the ground. A huge dust rose up. And then the lion, actually confused, he lost some consciousness for a bit, and then he looked through the dust, and then he saw the elephant is still looking at him. And then the lion said, if you don't know the answer, say you don't know. Now you know who is the king of the jungle, don't you? Now you know the king of the jungle. So today, ladies and gentlemen, I'm very privileged to introduce the real Michael King. So let's give him a round of applause to welcome Michael King. Now he was here for those of you who don't know, for over 30 years. Headed the EOS project, one of the biggest missions on Earth. And he's going to talk about a lot of other issues, and I won't go into the details. So please pay attention. We're going to hear a lot of very interesting stories about Michael King, the real king. Okay, Michael.
Okay, well, I didn't expect such a large crowd here day before 4th of July, but I know nobody at NASA can travel anymore, so everybody is here. So I'm going to give you a little bit of the background. Sometimes people, especially younger, think things were easier. There was a nice logical path and progression of one's development. Also, many scientists, one assumes, grow up doing school projects and science fairs, engaged in science. In my case, that was not the case. I really didn't become interested in science really till junior in high school. So that's unusual in that sense. But my father's executive, I lived in lots of cities in the country, he was president of corporations. And so I'd go from one school, 3 years, go to another school, different state. Every school thought that their school was better than yours. So I was put down in the middle group, and I moved up to advanced class, I moved to another state. So I remember being in Long Island in high school and taking some national exam in math. I had the highest score in the math in the school, and they were really embarrassed because I wasn't in the top math class at the time. So I really didn't take physics until high school, and that's where I got interested in going into physics. So I'm going to talk a little bit about the path through science, some of the scientific both breakthroughs and changes in the environment over time, which is pretty substantial. So I'm going to start out a little bit with some of the academic background. I went to college. I did go, like Claire Parkinson, Mike Freilich, several others, John Mather, to smaller liberal arts college, which is a very good grounding. And I'll return to the smaller liberal arts college background and how that's had a positive influence on my career in a moment. I went to graduate school later. This was during the When I was in college, it was there's this war in Vietnam going on. We got other wars today, but there was a draft, and I remember my fraternity house one night when they had the lottery. You could have heard a pin drop as you find out what your lottery number is for the draft, and I had a high enough number. I actually didn't end up going into the military service, so I went on to graduate school. I'll talk about some of this other stuff later. So Colorado College was at that time it is a small liberal arts college, 1,600 students. It's the base of Pikes Peak. The department chair at the time was Wilbur Wright, who was the nephew of Orville and Wilbur Wright, who never had children themselves, but their sister had son. And it was a very good program. And I would go and do a lot of hiking in the Rockies. There was a much closer collegial relationship with professors than I ever had in graduate school or elsewhere. We'd go to their homes. And so one of the prominent professors who influenced me was Dick Hilt. So Marcia McNutt, who was recently director of USGS, and now she's executive director of Science magazine, she was 2 years behind me in the same physics department. Jane Lubchenco was 2 years ahead of me in biology. There are a lot of prominent people. Ken Salazar went there. But it was a small liberal arts college, so I had a lot of diverse academic background. I was hired one summer to teach physics, relativity, actually to a lot of high school seniors, and we'd go hiking up in Pikes Peak and with the professors and with the students. And we'd go up in the mountains and my professor, Dick Hilt, would talk about why the sky is blue or why rainbows are red on the outside, or the different colors, or why the sky's polarized, the polarized sunglasses. So I got interested in nature. And I'd been an Eagle Scout and liked the nature. So that was one positive aspect of the atmosphere. So the thing at graduate school, I wasn't very interested in high energy physics and a lot of classic physics, but I was interested in the atmosphere. And one of the requirements they had as a senior was to do a senior seminar for the department. I'd never given a seminar. I didn't know anything about what I wanted to talk about in physics, but I had done a year with was given a gift by Dick Hilt, actually, the Feynman lectures in physics. And there was one really nice one in there on atmospheric electricity, lightning, charge electrification. Actually involved Lou Batten and people that I knew later, but it was on lightning, and so I gave a seminar on that, got interested. At that point, I'd actually even applied to graduate school and been accepted at the University of Arizona in physics, and not knowing at all that they had a graduate program in atmospheric sciences, atmospheric physics. So I went there not knowing. I went into physics and then transferred immediately to atmospheric science, but I took a lot of physics from Don Huffman, and people in rate of transfer would recognize, and others. But they had two people there, two professors at that time, who did research in lightning. One's passed away and one is retired now. But nevertheless, they had a prominent lightning program. Whoops. And so the first research I started doing was actually lightning, following on the Feynman lectures. And my professor at the time had done a theoretical paper, and you can probably imagine this, but calculation how using radar at X-band, 3 centimeters, could get enough signature to detect expansion of lightning column and be detected with radar. So he did this nice theoretical paper, and my job was to take measurements during the summer when I have all these lightning storms and to verify. And I would probably still be a student if I had stayed with him, because there was no detectable signal whatsoever. I did many lightning up on the penthouse and looking at lightning with this antenna with vertical, and there was just no way. And so I decided to switch to atmospheric radiation under Ben Herman, who's shown here. So at that time, I started doing ground-based measurements and theory. So for perspective on the technology, this is considerably predates Aeronet. This is the sun photometer that I used at that time, built by Glenn Shaw for his PhD thesis in 1971. You'd line up the sun through this hole and look for a shadow on this hole to get a line, and make sure this is actually pointing at the North Pole, and it would rotate through the sun during the day. And usually it would drift off. He had to realign it. It was not very easy. Probably the maddest I ever saw Ben Herman was he found out after several months that one of the math students, and not a physicist, had been aligning up the radiometer upside down, looking at the ground instead of the sun for some time. But the data were recorded on punch paper tape. That's what we had at the time, and then you'd go over to the computer center and get it, put onto Hollerith or a computer IBM punch cards and stuff like that. But it was mounted on the roof of the building, data recorded paper tape. So this was the first paper I did. It's actually in Ozone. If people don't know, I did work in Ozone. But it was by accident, really, and it ended up with having a big impact. At that time, there was low aerosol content in the atmosphere over Tucson. You could see the sun, and this is measurements of the spectral optical thickness as a function of wavelength, the wavelengths we had in the sun photometer. And the top measure is after you take the total optical thickness, you subtract Rayleigh. Well, you have this bump. Well, that bump is due to Chapuis absorption band, the visible ozone absorption. And I could have waited along, I'd probably still be a student, but at that time, the ozone was processed by the Dobson ozone spectrophotometers. I put in WMO reports in Canada, published once a year, these red books. And I could have waited a long time to get what the ozone was at the time. So basically, I developed it was a nonlinear least squares fit to actually vary the amount of ozone level, subtracting out different amounts until the spectral optical thickness would be smooth, because that's what the physics of aerosols would have implied. And so I varied the amount of ozone and got that. And you could not do this probably here, but places where there's high turbidity, but there was a low aerosol optical thickness, and there was a good sensitivity to this. Well, this was one of my other interesting encounters with Ben Herman. As I submitted a paper for publication without Ben's knowledge, he was my professor. He had nothing to do with the work. I published, I got it, and I got accepted, and I said, oh, you're supposed to pay page charges. I didn't know you had to do that. So I asked my advisor, can you pay for page charges? And he was about as mad as with that other student. He did not take kindly to not being part of the paper, but it changed my whole relationship with Ben, because he realized, as he think about, that there wasn't anything in that idea that came from him. He had no idea where it had come from, and so my relationship with him became actually much better scientifically. But it's an approach I probably wouldn't recommend to people, and I don't think probably any other student has done that since. Kurt Tomey was Ben's student. I don't know if Kurt's here. Yeah, but I don't think it's a pattern that's recommended. But it did change my relationship with Ben. The other thing Ben had done for a paper with John Delweezy is thought about how to use a ratio of diffuse to direct solar radiation to get how much radiation is in the atmosphere, to get how much absorption there was in the atmosphere. And I did lots of calculations of rate of transfer that Ben actually didn't know how to do. But so I did a lot of calculations of rate of transfer, which I couldn't do today. I'm too old. Of a diffuse to direct ratio as a function of how much absorption there is in particle single scattering albedo, surface albedo. So I did a lot of these calculations, and but found out, much to his surprise, that there was a strong dependence on the solution to how large and small the size of the particles were. So I started working on inversion theory, and those who are familiar with AeroNet and what it does, it has to take spectral measurements or angular measurements and infer through Federal integral equations what the size distribution of particles. This is the formula up here. But Ben had worked on that for quite some time and never got it to work. He had worked with theoretical data and never with real experimental data. I figured out that the trick was in the selection of something called the Lagrange multiplier of the constraint. I spent a long time figuring this out, working it out, and I wrote quite a famous paper in 1978 on that, which is Ben's most cited paper. But I wrote that, and in the whole paper, I was so interested in the physics, the properties. This is an example of spectral optical thickness and the size distribution on four 4 different days. And here the coarse mode was stay constant, and the fine mode was the accumulation mode was changing from day to day. And this is quite novel. And so at the time I wrote the paper, in the whole paper I spent 1 sentence talking about the Lagrange multiplier and a little bit of the trick. And didn't really emphasize. I emphasized the results, the science that I was interested in. And I got queries from several people, Bruce Forgan in Australia being the most notable today. And I ended up writing a whole paper on Lagrange multiplier and how that worked. That's also an insight in how science is done. So I wrote this paper on, it seems like an esoteric subject, how you select the Lagrange multiplier and inversion problem. And I don't think it was cited or recognized for a while, but now it gets a lot of citations. So it's been discovered. So there's a time delay sometimes in this. This was an old shadow band. This is the instrument I actually used for my PhD to measure the diffuse. We had a ring. I'd have to go up there, block the sun, measure the diffuse radiation, and move it across till there's a shadow across this ring. You measure the total and diffuse. So my thesis was around that topic, and the 2 appendices were the inversion for aerosol, optical, ozone, and the size distribution. And those are actually more famous than this. But those I needed in order to do the actual solution, because there's more sensitivity than Ben first thought. And so you can probably count on a couple of fingers how many people were hired directly out of graduate school to a NASA civil service position, but I was one. I was hired in January 1978. It was called the Laboratory of Atmospheric Sciences, or GLASS at the time. Dave Atlas was the lab chief or division chief, and he was the first, and he's here, he was the first director and creator of that lab. It was later renamed Laboratory of Atmospheres, and I couldn't begin to tell you what you'd call it today in the creative reorganization, structuring, and naming. But I was the first scientist hired by Dave when he became lab chief. I had no prior experience with satellites. I'd only worked in ground-based. I also done some aircraft work with what Penn State used to have an aircraft in those days. I flew that over Tucson, measurements, comparing it with LIDAR. Initially worked with Bob Kern in the development of IRBI and SAGE 2. So Bob was here, he had been Ben's student 7 years before me, and he was IRBI project scientist. He had some concepts for cloud remote sensing, but he hadn't finished most things. He needed some real help. So I came and worked with him, and I became project scientist when Bob moved to headquarters in 1983. And so I was project scientist at URBS. If you saw Warren Wiscombe's talk the other day, he showed the URBS satellite, which was launched by Sally Ride. Kathy Sullivan is now acting minister of NOAA, was the first U.S. woman to walk in space. She was on that same mission. So I've known her since 1986, 84. So anyway, I worked on early algorithms with this MCR, which Bob did develop, a multispectral cloud radiometer. It went first in W57F in 1979. Later, I gave it to NCAR when they were going to get the B57. I don't know what they've actually done with it. But anyways, the surprising thing is I learned at the 40th anniversary of Atmospheric Sciences at Goddard, here in this room, that Dave hired me, partly by recommendation by Arizona Department Chair Lou Batten. He was a pioneer in radar meteorology, like Dave, had been a president of the AMS, but he was Dave's roommate and best man at his wedding, which I learned from his wife actually at my house. So, and I never had applied for the position. I got called because of who I knew. And Dave had been really impressed with Ben Herman's early backscattering of melting hailstones, and was able to reproduce measurements he made in Imperial College. So there was a fondness for that. So early on, I started working on an interesting 40-year-old problem called anomalous absorption, which has been around, they changed names, but it's just the same story for a long time. I call it excess absorption by Ramanathan, but it was anomalous absorption, known 40-year problem, why clouds appear to absorb more than solar radiation can account for. This brings me to one of a couple that I have on Sean Toomey. This is a picture of Sean which the Bulletin EMS won't publish because I wrote the obituary, but it's not high enough resolution for them to publish. So, but Sean in his blackboard in his office would he sketched out and talked about the multiple scattering inside clouds and the so-called diffusion domain, multiple scattering inside clouds, and the multiple scattering amplifying the sensitivity to absorption. And so early on, I did a lot of work in asymptotic theory, which many people think is an approximation, but is a rigorous solution for really thick atmospheres. So this is the cartoon concept, and that is if you've got a cloud or plane parallel, even rough here, you get sunlight coming in, some is reflected, some is transmitted through, and if the cloud is thick enough, inside the middle of the cloud, it has very nice radiative properties. And those properties are that the radiation is peak straight up, minimum straight down, regardless of where the sun is. It's got the same shape, regardless of the sun. It's azimuthally independent because it's that way. And it goes for no absorption, somewhere between zero, no absorption, it goes as the cosine of the zenith angle, which is actually the assumption in the Eddington approximation. So it works Eddington works well for more low absorption, single scattering. High single scattering being a low absorption. So this was the concept. And that brings me to another complicated aspect. Early on, and you can't do this at Goddard anymore, but I had a concept of building this airborne instrument, which I called the cloud absorption radiometer, to measure radiation inside clouds. It's subsequently mounted on 3 of Peter Hobbs' aircraft. Peter has since passed away, but it was on P-23, which used to be the plane that Howard Hughes had. And the C-131 and later CV-580. It's flown also on these other planes, including the NASA P-3 out of Wallops. Had a lot of spectral bands. So I had the concept for the instrument, and it is the most heavily used airborne instrument ever built in-house at Goddard. It's still being used by Charles Katebi quite often today. There's a picture I took back in 1987 of the aircraft, and it was mounted in the nose of this plane during the Fire Stratus experiment in 1987. But I say you couldn't do this today. They had something called Director's Discretionary Fund, and for many years I was a Goddard Senior Fellow, and we would review all the proposals recommended to the director for things that are creative, high-risk, novel ideas. So there's no guarantee there would be an airplane mission to fly it on, but it was a concept that was interesting for development. Initial cost of this instrument, $59,000. It was built in-house, designed, assembled, aligned. Everything was done in-house. There was a lot of civil service labor with no full cost accounting, and this was the parts. So Tom Young, who later became President Martin Marietta, he was the director to approve this. Well, we built the instrument with no guarantee there'd be an aircraft to fly it on. In parallel, I wrote a proposal to NSF with Peter Hobbs to fly it in marine Stratocumulus clouds with no guarantee there'd be an instrument to fly. Both funded it. Got funded. And that's kind of a risk in both cases. It flew. And so the proposal several years later when we had real measurements, I'll show you, and showed there was no risk. That's the first time I got a grant from NASA headquarters to analyze it. After we knew the technique worked, knew there was diffusion domain, had measurements. So my comment here is that risk aversion has a long and distinguished history in NASA. But this Director's Discretionary Fund is not an opportunity that's available anymore, which is a shame. So one of the measurements we made back in 1987 with Stratus was the similarity parameters, no absorption to 100% absorption as a function of wavelength. So the curves here is a function of wavelength. Our theory for liquid water, the dots include with water vapor, and the symbols are the measurements I made at different wavelengths. So it's the agreement between theory and measurement is There's a slight offset, but they're not wildly off. It's not clouds absorb a lot more than the theory. It was small but present. So this is still pretty unique set of measurements. I took a 1-year sabbatical, went to the University of Washington. I taught graduate courses. I worked with Peter Hobbs, Conway Leovi, Jim Holton, Mike Wallace were all there at the time. And so it was a very, very productive year. But during that year, I went abroad to China, where I met a recently graduated Teruyuki Nakajima, that some of our friends in Maryland gave him a nickname Terry because Teruyuki was too complicated. And he's gone by that ever since. I gave him a keychain with the name Terry, and he liked it. So this actually was in our house for his going away party in 1988. So the work we started doing was to derive a technique for determining how large and small cloud droplets were, the size of particles in clouds using multiple scattering, and also how optically thick it is. So this is quite a well-known figure showing how the reflectance of a cloud, actually the ocean can do the same thing, but this is a cloud optically thick at a shortwave absorption channel where water absorbs radiation versus what it would be at a non-absorbing visible wavelength. And basically theory shows that at a visible non-absorbing wavelength, the cloud more bright it is, essentially its optical thickness increases 16, 32, 64. This wavelength where there's absorption, the brighter cloud is small drops, and as it gets more and more larger and larger drops, absorbs more and is darker. And so you have a perfect remote sensing problem. You have almost orthogonal information. Two wavelengths tell you two physical pieces of information about an environment. And these are real measurements we made in San Diego. So we were able to obtain the first diffusion domain measurements. The value of this field experiment was enormous. And actually all the well-known published papers were for 1 day of this experiment. They would obtain first diffusion domain measurements within clouds, retrieve the spectral absorption. We used the reflectance property of cloud to determine the basis for the optical thickness and particle radius. And we also flew through clouds modified by ships, so-called ship tracks. And this was also actually on the same day. This was published later in Science and other places. So Sean, who had a habit of not attending conferences and not a published job, he didn't like to go out unless there was a horse track around. But I invited him to San Diego, and he came out to the airfield. It was North Island, Naval Air Station North Island, which is Coronado Island, San Diego. He visited San Diego to see the University of Washington plane. I gave him a tour of the instruments, described things to him, radiation, and it happened to be the day we flew through ship tracks, which is the Toomey effect, the indirect effect of clouds. And he attended the mission planning meeting. He came into the back of this trailer, and it's like anybody's done field experiments, they're always pontificating about what we saw, what we're going to do tomorrow, you know, this random speak. And they're talking about the Toomey effect, the indirect effect of clouds and stuff. And Sean's in the back of the trailer with me listening to all this. And the only people in the trailer who knew him were Eradicate, Jim Coakley, and I. Everybody's going on, nobody knew he was there, he didn't say anything. Later at dinner, Sean and I, had dinner, and Diana was there too. He was talking about his experience coming from Australia to the US. And he was somewhat, if you knew him, kind of a cantankerous Irishman. But he was in CSIRO at the time, and he was coming on sabbatical to the University of Arizona. And he wanted to bring some instruments through customs. This is sort of a Brent type thing. He'd come into customs with instruments, want to get through customs and not pay duty, I think. They go to this big computer printout, and they couldn't find a list for this instrument called an Aitken particle counter. So, well, it's not listed on my computer printout. And so Sean says, here, do you want it? He says, no, it's heavy, it's big, must be worth something. I'll charge you, and he just made up a number, charged some duty, which irritated Sean. Oh, he asked him if it was known by any other name. And Sean knew it was a Aitken particle counter, known another name, it was called Submarine Sniffler. But he decided not to tell that to immigration. because it senses the small particles that are condensation nuclei. But he was an interesting character. Early on then, I was, in 1988, there was a solicitation, announcement opportunity for the forming of the EOS science teams. Initially, it was develop algorithm, well, the atmosphere part, developed algorithms of cloud mask, radiative properties, and microphysical properties of clouds using a technique I described, aerosol properties, etc. Initially, the team members included me, Jorm Kaufman, Didier Tanner, and Paul Menzel. Later, Bokai was added. So it was a very small group of people. And I didn't know that Jorm had applied for the team. His office was 2 doors down from me, but we both had applied. And the way the AO was written at that time, 1988, for facility instruments, which is what MODIS was, is you could be a PI, you could have no co-Is, and you had to have an algorithm. So each of us had to have a well-defined algorithm. Mine even included polarization, which was later cut out of the MODIS instrument. Later, I was invited, one of the fringe benefits of this program. I was invited to lecture at the Enrico Fermi School of Physics in Verona, Italy in 1990, Lake Como for 2 weeks. They paid for me and my wife for 2 weeks. We lectured in this chapel, late 12th century villa or monastery. And the paper I published in that lecture ended up winning the prize paper year for IEEE that year. And actually my granddaughter's named Verona after that town. Early on, we also did other field campaign with Peter and Larry Radke, Peter Hobbs. This was a photograph of the Kuwait oil fires. This is the University of Washington plane. You see it's got a lot of engine on the nacelle. This is a reciprocating propeller. It's not a turboprop. And if it doesn't have oil, that's when you worry on this kind of a plane. And then this is the in-car elector, which doesn't exist anymore. And this is flight over the Kuwait oil fires. This photograph is taken by National Geographic Society, this particular one. And so one of the prominent things over Kuwait was, and nobody knew why, is there were white smoke and black smoke in the oil fields. Nobody knew why until we went through and sampled it. And the black smoke consisted of what you'd expect, spherical particles of chain aggregates of soot. The white smoke is cubic salt crystals, and probably a Persian Gulf getting into the table. And then they mixed into this grayer pall of smoke that looked like this. First of all, it was capped by an inversion, didn't get lofted in the stratosphere like Carl Sagan thought. There's no nuclear winter. It kept it 3 kilometers in height and stuff. Another side story is this particular plane, you probably couldn't do this today, but it was unpressurized, had a hole in the bottom of the plane. It was to have a laser shooting down. The laser didn't work, so there was a hole in the plane. And so we're flying over the Persian Gulf. I was with Peter Pawlitzki. It was his first field campaign. I'm eating an apple. We're both watching. I dropped the apple core down the hole of the plane, and thinking it was going to go in the Persian Gulf. It went down and shot out the slipstream and shot out behind the plane. But this probably, Piers might do something like that, but open a window. But it's not a. Okay. So early on, actually the first week, Gaussian Esser, I think, came to NASA headquarters. I had to do a briefing at headquarters because I was wanting to develop an airborne simulator for MODIS. There were some companies that wanted to simulate everything as a basis for all of the development of algorithms. And having done a few field experiments, I had respectable skepticism to simulating everything in a real environments. So I wanted to build an instrument. And so we later built this phone all over the place. I won't talk about that. So this is the early, 1996 MODIS science team. Vince retired. Murphy's retired. Jorm is deceased. He's retired. So there's a theme here. It was a long time ago, but it was a relatively small team. There were no co-Is. Vince Salmonson was a team leader. I've been the team leader of MODIS for the last 4 or 5 years. But Wayne Assayas, you may recognize some people. Mark Abbott is a dean. Anyway, So it was a fairly small team at that time. I came back from some experiment, I think the Azores, and Vince asked me, wanted to talk to me about 3 different positions, so I was interested in any of them. One was EOS Senior Project Scientist, one was Deputy Team Leader of MODIS, one was Head of Global Change Data Center, which runs the DAC. I had no interest in the latter. I thought at MODIS Science Deputy Team Leader would be more amenable, so I did that for a while, but then later became a Senior Project Scientist in 1992. This was a nervous time, though, when I was appointed EOS Senior Project Scientist, because my appointment, it was a different era. There's something called NASA Accepted, which is more than GS-15, but different than SESs, and Center Directors used to be that. Well, I had to go in NASA Accepted for a while, which, among other things, meant revoking your right to career tenure. And I did this for a while until I got SST, and that was signed by Dan Golden on Election Day between George H.W. Bush administration and Bill Clinton administration election day. And Golden had been appointed by Bush. He actually stayed through Clinton. And now I've had conversations with him. He's just enthusiastic as heck about some of the work that Claire and I did in that book, for example. But at the time, he wasn't known for his favoritism towards certain things in earth science. I think he's changed a little bit. And then Gossam was appointed program scientist in 1991. So the 2 of us did a lot of the leadership early on. So there was an interesting structure of the EOS program, and peers will remember all this. There was a IWG, Investigators Working Group, consisted of all the IDS PIs, which included peers as one of them, instrument PIs, facility team leaders, but not team members, the U.S. COIs of foreign instruments. To function properly, we formed a payload panel where we had to go through a lot of fits and starts and adjustments of payloads as budget realities started to hit. And so I want to take a few minutes to explain some of that history. It's hard to do all of this in a short period of time. At the time, the EOS AL came out in 1988, and we were selected in 89. Several things are different today than then. And I talked to Len Fisk. I'm on a committee with Len Fisk, who was the associate administrator who selected us. At the time, I commented that I can't imagine NASA doing this today, but Pierce Sellers, me, Mike Freilich, Steve Running, Chris Justice, we were all in our mid to late 30s. We weren't yet 40, all of them. Oh, early 30s for you, sorry, you're a child. But we definitely, many of the people were younger than 40 with the expectation they can run for a while on this program. And I think that was prescient. And so several of us are still keeping, not all retired, some of us are working. And I think that was something I can't imagine NASA doing today. And Shelby Tilford has probably had a role in that. I asked Len about that when I saw him last time. And he said you had to remember, he was only 45 at the time, so it didn't seem as young to him. But he doesn't think that the age explicitly played into their selection criteria, and it probably didn't. We probably were peak productivity and publication and stuff, but anyway, I just can't think of the NASA today doing quite that. But nevertheless, the other thing we did in this payload panel, which was different, I talked to Lynn about that too, because it was very collegial as we'd go through all this stuff I'm going to tell you about in a moment, where it sounds like EOS had lots of money and it was this wide open program, but it was tortuous to live through it, at least from where I sat. It was not as smooth as it looks like with rear view mirror. But we did a lot of things openly with payload panel and collegial discussion with different oceanographers, terrestrial ecologists, different disciplines, cryosphere folks, that was full and open. In fact, even Charlie Kennel allowed the OMB investigators, they came in the back to watch because he was presenting to the investigators some of the science and some of the cost, dollars associated, so they make intelligent trade space. I asked Len about that because there's still FACO laws were in existence, but they were ignored. He said we basically did the payload panel, we didn't go to the federal advisory laws, which are very restrictive. You have to be a temporary federal employee, you get badged and go through background. Anyway, so we just did this collegially, but it built a lot of community between different disciplines. And Barry and Moore was masterful at leading many of these, I think. So the first thing happened, the first sense of reality is the EOS program, when it was sold, was $17 billion through 2000. And the first restructuring, these are all synonyms for reductions in budgets. There was rescoping, rebaseline, rescoping, and all. But first went from $17 billion to $11 billion. We were to ensure continuity of operation over 15 years. That was a sacrosanct 15 years. Find multiple smaller payloads, not the large platforms. It was AM and PM concept was adopted, later became known as Terra and Aqua, and 7 instruments were deselected. So this was the first major process. Initial EOS program was also to be serviced from the shuttle, and actually in polar orbit. They were building another launch pad at Vandenberg, which got canceled after Challenger. So then the ink wasn't dry in that. In 1992, we were further reduced from $11 to $8 billion. The common spacecraft developed Aqua and Aura, which is the common spacecraft out at TRW, now Northrop Grumman. Higher instrument was deselected. Number of at-launch data products were reduced. So there was quite a bit of turmoil, and I won't go through all of these, but they had different groups on engineering and science, and I chaired probably all of them. Peers, all different project scientists were on there. Gossam was involved. We do different trade space, and it was collegial, but it was also tortuous. At one point, there was a mission EOS Color, short-lived, and then it was canceled to become the Symbiosis validation program without another launch vehicle. Landsat 7 was added to the EOS program. By added, meaning it was included in EOS with no more money, and its partners in DoD and NOAA dissolved. So we got the responsibility, but no more money. So anyway, so it's not as clean maybe as it looks like in hindsight. I established the EOS 24 measurement concept, which had kind of a life of its own other than what it was planned. I did this at Charlie's request because at the time, if you go back through history, you'll see we had some magical 24 instruments in EOS. And so we made sure that everyone had a unique role at some point. So anyway, there was a lot of documentation to stabilize the program, a science plan, executive summary. There was many versions of reference handbook. This is the latest one with Parkinson and all. And then we've had data products handbooks describing what to expect and what the data products were and how to find them in samples. The other thing, which may be a legacy people will throw darts at me for, but I created the ATBD process, algorithm theoretical basis documents. And we had a number of reviews, 7 different reviews, 2 for Terra, 2 for Aqua, 1 for Aura, 1 for ISAT, 1 for OMI, which we had both national and international colleagues review the state-of-the-art, the algorithm procedure and the process. So we did both written and oral reviews. Now today seems to be all the ROSA proposals are only panels and never written reviews. We did both, and we had people from different countries in every one of them. It was Japan, Europe, New Zealand, and we had money, and I paid them to come in. The purpose was to enable colleagues to provide input to refine the algorithms and to get community consensus on the approaches. And that was the intent. Now, some of the investigators have continued to update theirs with new version release voluntarily. They have been used for teaching. Some of them are really out of date because they don't describe the current event, but they were very helpful in the development process. So there were 10 missions in EOS, 10 different satellites, not all of which are still operating and flying. This is the chart of all of them. This is something I actually prepared at Ed Weiler's request a couple of years ago when he was director here. He was interested in showing headquarters that large missions had to considerable value, like Hubble Space Telescope here with a lot of spin-offs and a lot. So this is one chart of many in there of the science, but also it shows evolution over time of both the dollars. This is dollar K, so $20 million up to 100 and some million. This is only algorithms, calibration, validation, which are the part I had large responsibility for. And in 13 countries initially, we support a lot of graduate students, postdocs. This is when full cost accounting came in, and for some reason, full cost accounting may be more, but the budget hasn't continued to go up. And this stopped when I did this chart, which is before I retired, and I don't know how one would even do something like that today. But there was serious money for the investigations, but there were a lot of investigators being funded, a lot of students, a lot of support people, and it was and is quite a remarkable historical achievement. So MODIS, probably everybody in this building is pretty familiar with. So I'm the team leader of now. But MODIS was one of several instruments on the Terra platform and Aqua. Terra, as an example, as a whole platform, cost $1 billion, $100 million to launch an Atlas 2AS in 1999. Missions today cost a bit higher than that. Not even counting VIRs, but other instruments. It's just really become a very expensive business, lots of reviews, lots of engineering. And this was the first one quite like this, but it had 36 spectral bands, there's lots of capabilities you all know about, and 12-bit digitization. So it's been used for things not anticipated. One example is Christina Schu's using some of the ocean color bands to develop a deep blue for aerosol over deserts because it's high bit digitization and does not saturate. So it's got some really nice characteristics. Okay, need to wrap up pretty soon. So the other thing we did was to do some field work. So the biggest initiative for Terra validation was Safari 2000 initially. One of the nice benefits of this job is we got to go to a workshop in the third largest canyon in the world. This was the view out the balcony of the place I stayed. And we had a workshop with many different countries to formulate what we're going to do in Safari 2000. NASA sent the NASA ER2 aircraft. Maybe this one's better. University of Washington CV580. South African Weather Bureau provided 2 planes. And then that's also where I met Charles Gatebi, who was a lecturer in Nairobi, but he's working his PhD in BITS in South Africa. So this is some of the biomass and burning environment, and we did many different aircraft. We had open days. There were towers in 3 different countries. There were ground sites, there were aeronet sites, lots of different places. There was an outreach day or opening day, and I spoke along with the minister of South Africa, and later then got anybody who lost this stuff in South Africa. This is a picture. I wish I had a different one, but this is one I've got. I was invited to speak at a big thing with heads of agencies and spouses, a tuxedo banquet in Johannesburg, where the big observatory. And so I'm there in a tuxedo, Harold Anagar in there, my wife. You wouldn't believe it, but Steve Platting was in a tuxedo too, but he took his off so quickly I couldn't get a good document that for evidence he ever wore one. But Steve Platting and Bob Swap also rented tuxes there. I brought mine from South Africa, from the US, but that's a different story altogether. Later, this is the President of South Africa, Jacob Zuma, and that's me at a cabinet meeting, in which I this is presenting a MODIS image of South Africa, but I briefed the President and the cabinet. He's been in the news recently because he's been reporting on Nelson Mandela's health there in Pretoria. So we have done things with one of the aircraft engines, with the car instrument, not only for the inside clouds, but a lot of surface reflectance work. And I don't have time to go into all those. This is pretty interesting, though. One of the things we did to look at the reflectance property of different vegetation. Savanna vegetation, which is in South Africa. This is a polar plot, and like a lot of vegetation, it has a hot spot or backscatter is brighter than forward scatter. So this is what you'd expect for vegetation in the hot spot. This is ocean with sun glint, which has been compared with Cox and Monk reflectance properties for the ocean. There's a nonlinear scale because of that. This is water clouds with a glory and rainbow over Namibia. So there's different differences we measured in the atmosphere. This is the one that's really unusual. This is the Atasha Pan in Namibia, which is this. It's a big, large expanse in the northern Namibia. So it's unusual because it's dark in the forward direction. It's very bright in the backward hemisphere. There's no vegetation. It's flat desert. It's not Lambertian. And so my wife and I and Steve flew over this site. Most people take hours driving up there. We had a small plane and a pilot that landed us there at the Atasha. We went out in this, and Jim Butler found it. He didn't throw anything away. I found in his office yesterday this bottle, Oasis mineral water bottle I had, and these are pieces of the sand from Atasha Pan I picked up in Namibia, put in here to bring it back here for him to measure in his bidirectional reflectance lab here in this building. I'm sure this was illegal, but we have measured the BRDF in his lab, shown the backscatter of this material, and have published a paper on that as well. So anyway, so we did that. I think I'll skip some. This is kind of well known. This is all the cloud optical thickness of particle radius. This is a MODIS image, stuff we've done a lot of. It's all over the place. I did work on, this is, people may be interested in this. If you look at a satellite view of the surface reflectance, so the ocean's not here, but at one particular wavelength, 0.86 microns, and the desert is bright, there's a lot of clouds here, there's missing stuff. So this is, we have a clear sky view of the surface, different look angles, and get the albedo, or the reflectance of the surface. There's a lot of part of the land surface where there's no observations. Because of clouds, because of, so July, the Indian subcontinent disappears because of the monsoon, this kind of thing is cloudy a lot. And so we did work here with Eric Moody, who worked here at the time, doing senescence and growth and time series analysis all over the world to get a gap-filled, complete surface reflectance product without snow, and then we overlaid snow on it later. So this is used in the ECMWF, which is the European Center for Climate Medium Range, or the forecast models in Europe. And it's used actually in AeroNet for surface reflectance in their inversions, and it's very, very powerful. This is reflectance of snow by different surfaces, showing that the tundra may be bright in the visible, but if you're over evergreen forest, like appears like the boreal forest in Canada, a lot of tall green trees, the effective albedo is much, much reduced. So we've also published that. So again, I'll probably skip this is actually the paper I just recently published with Platnick, so I'll skip some of this, but properties of clouds globally, liquid water and ice clouds, and stuff we've done with MODIS over the years. Those and a lot of other global products, people look at the mean of some property, and many properties are not, sorry, this is over the entire globe, cloud optical thickness, and it's highly skewed. The mean may be 16, but the mode is 4.5. There's a lot of thinner clouds, a long tail, so you have to look at context of what you're looking at. And so one of the things we're going to put in collection 6, I believe, or my expectation, is to put in a median, not a mode. Mode's too hard, but median, as well as the mean of some of these properties to take advantage of the fact that we have skewed properties of the environment. I'll skip that. This is kind of important. So we did work so one of the things you can do with MODIS is looking over regions of the globe. So this is an area off the marine stratocumulus off California. And this is the relationship between cloud optical thickness and effective radius for Terra and Aqua. And you see that they're basically positive correlated. So as the cloud is thicker and thicker, you get larger drops. If you had the Toomey effect or indirect effect, it would go the other direction. So this is over a whole month. There can be different meteorology coming and going. There are different things. It's over a many degree grid space during the marine stratocumulus case. So it's a data set that does exist and enables detailed quantitative analysis that is somewhat novel in the satellite business. The last topic I'll turn to briefly is Oleg Dubovic, who's well known here also. I first met him in Belarus right after he had gotten his PhD, or a year after he got his PhD, so he was a young postdoc. And I flew to Minsk, and I was told in an hour the department's coming to hear your seminar. I said, what seminar? They never told me anything. I didn't have any view graphs. There's no laptops. And but they thought if they told me I was going to have a seminar, they'd have to pay for me, so they didn't do that. So I showed up, and Terry Nakajima was there too, and he had some plastic view graphs and no laptop. So I used some of his, and Oleg was a designated translator. He'd translate between English and Russian as we're speaking. Anyway, so that's where I met him. Then later, he had a postdoc in Japan, and I brought him to Goddard and introduced him. At that time, he didn't know Brent Hoban or Yoram Kaufman. I think he met P.K. Bartia in Fairbanks, the RS. And he stayed at my house for several weeks. And at that time, he found lecture notes where I taught remote sensing inversion methods at the University of Washington for many, many weeks. We started talking a lot about inversions and nuances of retrievals and stuff. So we had very intellectual discussions. So later, we developed all the aerosol size distribution signal Albedo retrievals algorithm for AirNet. And I won't go into the details here, but this is an example of one place in AirNet. So it's new measurements from Airborne. It's a Manga Zambia, but it's spectral optical thickness are the data points with error bars, and that's how the analysis reproduces the measurements, is the smooth curve. This is measurements made along the Albedo, which is the same view as the sun going around the horizon. So the sun has to be not the zenith, but down a ways. And this is a scan angle of that different wavelengths. And then we can use that information to retrieve the size distribution. This is volume size distribution, not number, like I showed earlier, versus radius. And this is the refractive index, real and imaginary part, and you can't read that, single scanning albedo. So this is it's widely known papers that are often published, but it's often referenced, but I think a lot of people don't read the papers. They just know that's to read. So recently I wrote a book chapter in a textbook dedicated to the memory of Yoram Kaufman, and it's a detailed chapter on all the inversions from first principles and all the mathematics that you can't really do in a journal article, really. And so it's very complimentary, but Oleg and I did that. This is a well-known paper with over 900 citations. So this is a work that I did with Claire over a period of 7 years. Is that right? Something like that. And others doing this, Our Changing Planet. And we're the lead editors. Peers wrote both the foreword, and he thought it needed an epilogue or a summary. It's very comprehensive and very widely regarded. This is the one that Dan Golden is in love with, but you wouldn't have known at the time he was at NASA. After I retired in 2008, I did go to the University of Colorado. This is almost a view from my office. Anyway, the lab I'm in, LATH, is similar in nature to what Goddard has traditionally been. It's a relatively small lab with scientists, engineers, clean rooms, high bays, managers, administration. I continue to publish. I've done more community service that I couldn't do when I was at NASA, sometimes NRC committees. One of which, with Len Fisk and Nez Fung and others, will formulate the next decadal survey for Earth science. So it's kind of important, but it can be a lot of work, and that will be coming up in another couple of years, 3 years they'll start it, something like that. So final thoughts. I want to go back to liberal arts education. I remember having a very vehement argument with one of my colleagues and his students in the audience, I won't mention who he was, about differences between the different educational systems. And at Colorado College, I did a lot of English, history, I took economics, accounting, as well as physics and biology and ecology. And so I think that a lot of my ability as a scientist, both for public speaking, for writing proposals, communication skills are very broadly based in, and I got a lot of that in the liberal arts school, and I think that's very a positive thing. I say Mike Freilich has the same background, Ann Thompson and others. Career path included rate transfer theory, airborne instruments, ground-based instruments, and satellite work. I also want to mention that this is not done alone. There's a large team of people. My most frequent co-author has been Steve Platnick, 22 papers. Apparently, I had to go back and check. That's my most frequent collaborator, but I've had 229 different people over the years. Management at EOS was not easy exactly, in spite of what it may appear with hindsight. But I had a lot of opportunities to public speaking, audiences as large as 15,000. I've lectured in 32 countries, 7 continents, press conferences, TV. So there's a lot of that's not a standard background and career path of many scientists. And I was thinking there are 38 different project scientists over time, but I think it's more. I forgot Gene Feldman, Chuck McLean, and EOS Color. I may have forgotten another EOS DIS, I can't remember. I think Bob Price was EOS DIS at one time. So there's a lot of people who have been big part of participating in making this program quite successful. The future of Earth, I do think we're in the golden age of Earth science. Missions formulated the decadal survey are as complicated, and I don't know how we'll make something happen. Certainly not, it's a multi-decadal survey. I don't think this will happen in one decade. Cost estimates were, to me, they were dead on arrival. I knew some of the costs were unrealistic to me at that time. There was a midterm assessment by the Academy. Bill Townsend was on it, several other people emphasized the need to interpret the decadal survey as relative level of investments and also have cost constraints. And it also recommended a payload panel mechanism because it was very helpful in EOS. This is roundly rejected by headquarters, by Grunsfeld and Freilich, who don't want that advice. And Freilich lived through it all. He knows exactly what the process was, but does not want to implement that kind of thing. I don't want to be in the ESAC advisory committee because that's a FACA thing with financial disclosure statements and temporary employee that's not paid, and I just don't want to do that. So there's complications in the FACA process today, but in any event, the planning process will commence in thought process in September, and I don't know what the next future will bring, but that's what I've got. Thank you. Oh, Piers was the first project scientist I appointed when I became EOS Senior Project Scientist. And it worked out pretty well until he went off to want to fly in some higher level.
Promised me a pay raise.
Actually, took a demotion to go to JSC. Got busted. Yeah, you had a question?
Well, you mentioned in the about the Kuwait fires. You talked about the inversion that held the smoke down, and mentioned that negated the nuclear winter theory. But that's not something you could count on in all large fire regimes, correct? Or
correct. You can't count on it. So what happened in Kuwait was several things. First of all, there's this. Well, actually, wasn't in the U.S. news in the last Kuwait war, but there's always a period of time in April when they have the shamal. They have this low pressure and circulation from Iraq, and it comes down and blowing things from the northwest, southwest, paralleling the Persian Gulf. And there was a well-capped inversion, and also there was a lot of sand. So what happens is you had the white smoke and the black smoke that formed this gray pole, so it wasn't as absorbing as people had thought. So it didn't punch through the inversion layer. And also there was a lot of sand from the shamal, and the Kuwait smoke particles stuck to the sand and gravitationally settled out. So it didn't last as long. But there's still 580 fires going when we were over there. But it's a well-capped inversion, and it was well-capped, and it was like 3 kilometers and flat, as you saw in that picture, and it was also 50 kilometers wide. It was like a snake in the desert that moved by the winds in the day, paralleling the Gulf. That was one of my early experiences with media too. I was doing a lot live interview on that, and I was just extemporaneously said like a black dragon or snake in the desert. She cut that out and used that in her own wrap-up and summary of the broadcast. We call it plagiarism in science, but what do I know?
So with that, of course, you have any other questions or comments, might be here for a few minutes. And so expect to see you on 15, okay?